So it is our great privilege to have Dr. John Mather with us today in the 26th AABEA Technical Webinar Program. So welcome to each and every one of you. Good afternoon, good morning, wherever you're joining from. I'm Anis Rahman, host for this technical webinar where we are extremely fortunate to have Dr. John Mather with us today. So I have just one or two slides for introduction, and then we'll go to Dr. Mather's talk. And the brief program note is that after the brief introduction, Dr. Mather will present his keynote talk, and then we'll have open Q&A by moderation. And Dr. Mather doesn't need any introduction, as you all probably know, and of course you know, he's a world-renowned scientist, senior astrophysicist at the NASA Goddard Space Flight Center. And his work on James Webb Space Telescope started from the very beginning of the JWST project. And even prior to that, he started working on the Cosmic Background Explorer Program, or COBE. And he is the principal investigator for the Far-IR Absolute Spectrometer on COBE program as well. So with the COBE team, Dr. Mather showed that the cosmic microwave background radiation has a black body spectrum within 50 parts per million. And this is so important, as you will learn during his talk, because this confirms the expanding universe model to an extraordinary accuracy. The COBE team also made the first map of the hot and cold spots in the background radiation, showing the anisotropy. And for all of these works, Dr. Mather received the 2006 Physics Nobel Prize, along with George Smoot, and primarily for their discovery of the black body form and anisotropy of the cosmic microwave background radiation. I had a good fortune of meeting him in person here at Dickinson University, where among many prizes Dr. Mather has received during his long career, the Priestley Award was also given to him at Dickinson College. And Joseph Priestley, the discoverer of oxygen, actually was a friend of the founder of Dickinson College, where a lot of the original instrument Joseph Priestley used is there, housed in Dickinson College here in Harrisburg, in Carlisle, Pennsylvania. And every year, they arrange a Priestley Award program where I had the good fortune of meeting Dr. Mather earlier this year. So without further ado, it's my extreme honor and great privilege to introduce Dr. Mather to you. And the floor is yours, Dr. Mather, please.
Oh, my goodness. Thank you so much, Dr. Rahman, for the introduction. I will now attempt to show my my view graphs so that you can see my story, but I can't do that yet until you let go.
Oh, sorry. I'm sorry. Yeah. Okay. Sorry. Please go ahead.
Okay. One moment, please. It was a pleasure to meet you, and I'm always delighted to be able to follow up on those kinds of introductions. So, do you see my slides now?
Yes.
Excellent. So what I'm showing you here is the picture of the Great James Webb Space Telescope as we imagine it is in outer space, although in reality it would be in darkness and we would not be able to see this picture. What we see is a gigantic golden hexagon It is 6.5 meters in diameter. It is made out of 18 smaller hexagons, and that is the primary mirror that collects light from distant stars, planets, galaxies, and the most distant objects we can find in the universe. It's all collected by this gigantic mirror and focused into the instrument package, which is located behind the mirror right in the center. The telescope is protected by a gigantic umbrella. We call it a sunshade. It is made of 5 layers of metallized thin plastic, and it's shown as gray in this drawing. It's as large as a tennis court. The project is a joint project of NASA with the European and Canadian space agencies. It was launched on December 21st of 2021. It took about 20,000 people to build it and launch it and get it going. It's available for use by all scientists around the world by sending us proposals. So the results will come out, and they are coming out regularly. So I'll tell you a little bit more about the telescope as we go along. But before that, I want to give you a little bit of introduction about why we're doing it. What are the big questions that people want to know the answers to? So for instance, where did we come from? What is the cosmic history of the universe? Are we the only living sentient beings or not? And if they're not, then where are the neighbors? Is life a miracle? Does it require an extremely unlikely coincidence for it to occur, or is this something that will always occur given the chance, given an opportunity? Of course, we also want to know, can we travel out of the solar system? And I'm afraid my answer is, well, we can get as far as Mars. We cannot personally escape from the solar system, but astronomers and you and I can travel as far as we like through imagination and pictures. So I'm going to take you with me as far as we can with the imagination and the pictures today. So the beginning of science was over 2,000 years ago, and I don't know all of the things that were done, but we have one small booklet called The Nature of Things, as translated from Latin from about 2,000 years ago. Lucretius knew, as many people did at that time, that the universe could be made of atoms. They had a name, and it meant a small indivisible particle. They had evidence already, which could, for instance, include the fact that a glass of water can disappear by evaporation. So one way that could be is if it's made of tiny invisible particles. So people understood a little bit, and they did not yet know that there were the many kinds of particles that we have today, or that we would have nuclei and electrons and all the other parts. But they did recognize that structure could occur by combining the parts, and then they would grow, and then they might disintegrate and disappear, and that would be the end of those particular objects, as the atoms would separate into be forming something else. So that was a long time ago. Now I wanted to tell you a little bit about my own story. This is the farm where I grew up in far northern New Jersey, not so far away from Carlisle. This is a research farm belonging to Rutgers University. My father was there studying cows to see if we could get more and better milk from cows. And the answer is yes, we do have better now than we did then. For me, as a child growing up, it was a place to look at the sky, to learn astronomy from books. The library sent their bookmobile around to the farm every 2 weeks, and I got all of the science books that I could get, and especially books about telescopes. So that was a long time ago now. So a little bit of history. Back in 1946, a few things happened. The World War II was finished, and Lyman Spitzer, shown on the left here, was working for the Rand Corporation, which was a big think tank involved in the defense effort. And when it was done, he wrote a memo saying we should build telescopes in outer space. They would be good for looking down for defense purposes. They would also be good for astronomy. We could look out. Later on, he wrote another version of the memo that said if you could build them big enough, you would be able to image planets orbiting other stars. So that's a good long time ago. And it wasn't exactly in 1946, but here is Sir Fred Hoyle, British cosmologist and brilliant thinker, who is the person who gave the name of the Big Bang to the expanding universe story that we have. And I think we have him to thank and to blame for the confusion that people now have about the expanding universe. Because when you give it that name, then people always will picture a small explosion in a pre-existing space. In other words, a firecracker. But of course, what astronomers see is an infinite universe, as far as we can tell, and it's just expanding in itself. So what we see is exactly the opposite of what people think of when they think of a Big Bang. Then in 1946, I also appeared. I am now 77. So people think that's an interesting picture. I actually don't remember. That was a long time ago. So what else happened? Well, in 1948, a couple of years later, the two gentlemen on the left and right were Robert Herman and Ralph Alpher, and they were calculating about the early universe. We already knew that there was a story of the expanding universe because we had seen measurements that showed that distant galaxies are running away from us extremely rapidly. They calculated that the heat radiation from the early universe should still exist, and it should have a temperature of about 5 degrees above absolute zero, which isn't too far off considering that the real answer is 2.7. So that was 1948. Now, in 1948, it might have been possible to detect the radiation, but nobody tried. So that went along, didn't happen. Around 1954, I was a small child and I went to the Museum of Natural History in New York City and I saw the planetarium show, and I learned that Mars might have canals. And was very hopeful that year that we might see the canals. Now, the canals, as you know, do not exist, but they were seen quite often by people. And so the current explanation is that those are images of the blood vessels in the inside of an observer's eye. So we were fooled. It's kind of too bad that we were fooled, but there is a reason behind it, which is that the Mars rotates around its axis in just a little over one of our days. So the pattern would repeat almost every night that you went out to look. So they weren't quite careful enough to notice that problem. Then in 1957, Sputnik went up. The Soviet Union launched a satellite which completely terrified the Americans because it made it very obvious that we could be attacked by nuclear weapons from outer space. And we were already quite concerned about the nuclear weapons. As a child, I was taught that in case of nuclear attack, we should hide under the desk. And it doesn't take an adult to figure out that that's not a good plan. So what happened then? Well, in 1958, the picture on the left is the copy of the front page of the charter for NASA to exist. Congress said there shall be NASA. And so we started NASA in 58. And pretty quickly, of course, we said, we are going to the moon. So we're showing you President Kennedy. And I don't know if I'm set up so that you can hear the president when I play this.
Yeah, you can probably.
Let's try it. Do you hear him?
You have to share the sound, I think.
Yes. I don't know how to do that. So I'll just have to tell you what he said. So President Kennedy announced that we would go to the moon within the decade, and that we would do this and the other hard things. And because it was hard, and he promised not only would we go to the moon, but we'd do all the other things that we thought were necessary to make a good world for us. So the person on the right is James Webb, the administrator of NASA at the time. and he was the one who figured out how to do the mission, and he almost got there. He had to resign before we were quite done, because you might remember we lost several astronauts, 3 astronauts, in a fire in the Apollo capsule on the ground. So anyway, he figured that out and made sure we had a culture of doing things more reliably, that we were sufficiently cautious. And to me, it is a miracle that we were able to go and send our people to the moon in 1969, only 11 years after the formation of NASA. So what happened then? Well, now I want to come back to telling the story of astronomy. Astronomers look back in time by looking at things far away, because we know the speed of light. So we see things as they were when light was sent out. To know how far you're looking, you have to survey the universe. We have 2 basic methods. One is trigonometry, as we could have done thousands of years ago. And people did know in many parts of the world how to do this. I know at least the Greek astronomers were able to measure the size of the Earth correctly, and even the distance to the moon, but they were unable to measure the distance to the sun at the time. The other method they would have understood quite well, which we would have said, if we can prove that those 2 candles that I've drawn here are identical, but one looks fainter than the other, we would say it's fainter because it's farther away. So now we can survey the distances of all astronomical objects, at least in some way. So we also want to measure whether they're coming toward us or going away from us. And nature has given us markers in the spectrum of light. If you spread out the light of the sun or an incandescent lamp, you get a nice little rainbow. If you pass the light through a hot gaseous material, then you may get particular wavelengths of light. And we see that when we observe the fireworks on July the 4th here. Particular elements show particular spectrum lines, particular wavelengths. And if we now look and observe a star, like the sun or some other star, we'll see similar marks. So usually they're dark marks across the spectrum due to the absorption of light by those kinds of molecules. And we see this similar pattern in distant stars as local, except quite often the wavelengths are all shifted to longer wavelengths. And we say this is because the object is receding from us at some enormous speed. So now we can not only measure the distances of objects, but we can measure their speed toward us or away from us. And in 1929, this graph was produced by Edwin Hubble, the same Hubble that we named the telescope for. The graph shows the estimated distances of galaxies on the horizontal axis and the velocity going away from us on the vertical axis. And you see there is a clear trend. If you divide the distance by the speed, you can calculate the age of the universe. The first time we ever knew that there was even the possibility of having an age of the universe. Previously, people would have guessed that it had no age at all, that it was infinite. So 1929, although it must be said that this was predicted previously in 1927 by Georges Lemaitre, who was a Catholic priest from Belgium, who also had a doctorate in mathematics from MIT. And so he did this by using Einstein's equations to predict that this should be true. Okay, so what do we do then? Well, skipping ahead, I had a thesis project at the University of California at Berkeley to measure the cosmic background radiation that had been predicted back in 1948. It had been discovered in 1965 in New Jersey at Bell Telephone Labs. And by 1974, I was a postdoc at NASA in New York City. And there's the location. I used to bicycle to work, and I lived in a little apartment on the west side. And supercomputers in those days occupied entire floors of buildings, even though we would now be amazed at how little they could do. At any rate, it was there that we proposed a successor for the thesis project. Here it is called the Cosmic Background Explorer, as we imagine it to be in outer space. It had 3 instruments in it, one to measure the spectrum of the cosmic microwave radiation and compare it with the prediction of the expanding universe theory. It had a second set of instruments to measure the hot and cold spots in that radiation to see it's equally bright in all directions. It had a third instrument inside to look for infrared light that might have come from the distant universe, from things that we didn't know about and could never see with a telescope, because we would never have a big enough telescope to recognize them. But at any rate, that's the COBE satellite as we imagine it to be in outer space. And here is the key thing that drew a special worldwide attention. 2 years after the launch, we were able to publish this map. This is a map of the hot and cold spots in the radiation of the Big Bang, as observed at wavelengths of a few millimeters. And the hot and cold spots are very, very faint. The temperature of the whole map is about 2.7 Kelvin, and the hot and cold spots, there are about 1 part in 100,000 of that. So about 30 microkelvin variations of temperature from place to place. When Stephen Hawking saw the picture, he said it was the most important scientific discovery of the century, if not of all time. Now, why would Stephen Hawking say that? Well, number one, we believe that the spots represent density variations of the early universe, and that the denser regions have enough gravity to stop the expansion of the material and pull it back to form galaxies and then stars, black holes, planets, and finally people. So we are here because of those spots, plus the action of gravity. Scientifically, we're also very interested because the spots come mostly from dark matter, and their distribution is affected also by the dark energy that we now have deduced but can never see. And the third reason is if we ever understand the cause of these spots, perhaps we'll begin to understand quantum gravity, which is one of the great mysteries of physics, at least for the max. Well, Einstein worked on it, he failed. Many other people have worked on it, and so far it's still a big mystery. So now what are we going to do now? Well, of course, I show my graph. I went to Stockholm, I received my diploma from the King of Sweden, and I've been celebrating and going on to the next project. The next project is, well, of course, the Hubble telescope was launched soon after the COBE satellite. It's now 33 years old and still working beautifully, taking pictures every day, thanks to the fact that we sent up astronauts already 5 times to improve it, fix it, repair its focus, and make sure it's ready to continue on into the distant future. As far as we know, it could last a long time before atmospheric friction makes the orbit decay and bring it back down to Earth. So there is a hugely difficult and successful space engineering project there with huge results on astronomy. Virtually every textbook on astronomy had to be rewritten after this Hubble telescope was launched and repaired. But in 1995, a committee was formed to write a book about what should we do next after the Hubble telescope. And they wrote a book that said, please build us a new telescope that's bigger and more powerful and capable of observing infrared light. So I will show you what is special about infrared, and many of you already know because of your work. But anyway, I'll just summarize why it's important for astronomers. Project is NASA-led by an organization here at NASA Goddard Space Flight Center in Maryland as an international collaboration with Europe and Canada. We have a very large aerospace contractor that works with us. That's Northrop Grumman Space Systems. When we chose them, they were still called TRW, but then they were acquired by Northrop Grumman. We have 4 instruments on board. Near-infrared camera that comes from the University of Arizona, makes a lot of very beautiful pictures that you've seen. We have a spectrograph that's produced in Europe by the European Space Agency with their contractors. We have a mid-infrared instrument that takes pictures and makes spectra, and an international partnership made that, including the Jet Propulsion Lab and Europe. And finally, there's a fine guidance sensor and another spectrograph. It's produced by the Canadian Space Agency. So the very powerful international partnership to bring all these instruments together. Telescope is operated by the Space Telescope Science Institute in Baltimore, Maryland, which is the same place that runs the Hubble Space Telescope and processes the data, makes them all available to the public, such as you. So which we've already said here, that the telescope is 6.5 meters in diameter. I didn't tell you yet that the telescope is cold. It's cooled down to about 40 or 45 Kelvin. So that it does not emit very much infrared light, and so that the detectors will be able to detect the infrared. It was launched on the European Ariane 5 rocket on Christmas morning, December 25 of 2021, and we planned to have a 5-year science mission, and we would be very happy if we got 10 years. Now it looks like we can get 20 or more years beyond today, which will make us extremely proud, and astronomers will be very happy to get all the data. Here it is being launched on December 25th. It was actually well after sunrise, but the camera has been adjusted to expose for the brilliant light of the rocket engines themselves, so you would think it was dark. But it was daytime, and we had a perfect launch. That's the reason why we have such a long predicted lifetime, because we use fuel for various reasons, and when the fuel is done, then the mission is over. This is where we sent the observatory, where it still is. There's a place in space called the Lagrange point 2. Actually, there are 5 Lagrange points in this Sun-Earth system, and these are places where an object can stay forever by balancing the gravitational forces of the sun and the Earth. So this particular one is not quite stable. It is 1.5 million kilometers farther from the Earth than the sun. Excuse me, it is 1.5 million kilometers from the Earth in the opposite direction from the sun, as shown here in the sketch. We actually do not go right to the Lagrange point because it's in the shadow of the Earth, and we actually need the solar power to run the observatory. But it's a perfect place to put the telescope because it's relatively near to Earth, so it's easy to communicate with it. And the single-sided umbrella, the sunshade, can protect the telescope from the heat of the sun, the Earth, and the moon very easily. So the telescope is cooled down to its low temperature passively, just by radiating heat to outer space. So now I want to talk about why we built a telescope to observe infrared light. There are numerous reasons. This is one of them. This is a picture taken by the Hubble Space Telescope at visible wavelengths, wavelengths you and I can see. And what we are looking at is a new star being born inside this amazing, beautiful cloud of gas and dust. And you can't really see it very well, but right here in the front is the star sending out luminous jets of material as it's being born. And with Hubble, we were able to do some infrared capability. So now we see the same location with Hubble, and we see that the dust cloud has become almost transparent. You can see through the dust, see the stars behind the dust, see the details of the star being born inside the cloud. So we knew immediately that an infrared camera would be able to see stars being born inside their dust. This is one of the great mysteries of astronomy. Obviously, there are stars everywhere, but we've never been able to see them directly in the process of being born. So that's number one. Number two, of course, many objects are not warm enough to emit visible light. But they're plenty warm enough to emit infrared. As an example, you and I are each emitting approximately 500 watts of infrared power, and we would be visible from a great distance using an infrared telescope. This particular object is called the Southern Ring Planetary Nebula, and it's seen with our images are taken with infrared equipment on the Webb telescope. The relatively short wavelengths on the left and the longer wavelengths on the right. So we're now able to see things that are not visible at all with the Hubble. In fact, combining two things, we're able to see right in the center of the right-hand side that the star that we thought was a single star disintegrating is actually at least two. The current opinion is there are 5 stars there in the core of this nebula. And what we're seeing is debris that is being expelled from the atmosphere of one of the stars as it's getting old. This is actually a very common thing. Almost all stars end their lives by sending out some of their material into outer space, and they look sort of like this. It's called a planetary nebula, although it only looks like a planet. It is certainly not one. So here's a magnified image of this as seen by the Webb telescope. So the third, just as an example of something beautiful we've seen with this technology, here are 2 stars orbiting around each other, and every time they get close together, one of the stars sends out a puff of its atmosphere into space, and we see this strange, not quite circular set of shells being produced by this interaction, as seen on the left. By the way, the data have been reprocessed on the left by an amateur image processing specialist, Judy Schmidt. She lives in California, and she receives NASA data and makes them look better. So you can see what they're trying to tell us. So the third reason to study infrared light is that the universe is expanding. We see distant galaxies running away from us at enormous speeds, giving what we call the Doppler shift. Another way of describing this is that space itself is expanding. But now, since space is not a thing or a substance, it's not made of atoms, for instance, it's a little tricky, but it's an interesting way to think about the expanding universe, that space itself could be expanding. So because distant objects are going away from us at great speeds, we need an infrared telescope to pick up light that started off at visible or ultraviolet wavelengths. So that's what the picture is trying to tell us here. Build an infrared telescope to do ultraviolet astronomy in the early universe. So now I want to show you some of the data we got. A year ago, on July 11th, President Biden released this image to the public, and it's beautiful for astronomers as well as for the public. It shows a number of things I'll describe for you. The stars in here, like this one, with a blue spike sticking out, those are ordinary stars here nearby. And because we already know about most of them, it's not a big surprise that they're there. We see also these huge fuzzy objects right in the middle. See if I can get my pointer to work so you can see it. So here we have a great galaxy in the middle, very bright, and it's important to us not because it's there, but because it has so much gravity, and it and its neighboring fuzzy galaxies, they all have so much gravity that they bend space. Einstein told us in 1916 that gravity operates by bending space-time. And he soon realized that the bending space-time would mean that a gravitational lens could exist. The galaxies in the foreground, the big bright ones, can magnify and distort the images of the more distant ones. So here we see several arcs of strange-looking galaxies. In this case, these 2 arcs are duplicate images of a more distant object. Sometimes we see 3 or 4 or 5 images of the same distant object because this lens is not one that we would design to be making a perfect image. It has multiple but imperfect images of the same thing. So Just to give you a sense of how much is light bent, you can see that light can be bent by several arc minutes just by the presence of a galaxy. And the typical light wave from the early universe has already been bent by 1 or 2 arc minutes by the time it gets to our equipment. So this is a laboratory for us to study the most distant galaxies we can find with the greatest possible magnification. So after we've found the most interesting ones, we do additional steps. We magnify the image. First, we find the ones that seem strange and different. We magnify the image as much as we can, and we also obtain a spectrum of each one, spread out the light into its colors to learn about its chemistry, its temperature, and the motions within it from the Doppler effects. So we're illustrating here that we are surprised by what we're finding. The early galaxies that we found are much too big, much too bright, seem to be too massive. They already have structure. Some of them already have spiral shapes fairly early on. So this was not predicted by astronomers. We're not yet ready to tell you why we were wrong. Right now, we just know that we were wrong. So this is a big puzzle coming. Here's an example of a highly magnified image. One of those little streaks has been so highly magnified that we can recognize individual star clusters. So each one of these little objects with a circle around it comprises maybe 100,000 fairly ordinary stars. And we see a couple of dozen of them in this particular early galaxy. So we astronomers are thrilled to see this, and we've called this one the sparkler because it has so many little objects in it. Here's an image of something we call Stephan's quintet. There are 5 galaxies in the picture. Mr. Stephan noticed this combination a long time ago. Now we know that the one on the left is all by itself, and the other 4 are all close to each other. The 2 right here in the middle are right in the process of combining, and they will, within a few 100 million years, be completely mixed together, and they will no longer be spirals. You see these luminous regions around them. These are new generations of stars that have been formed because of the collision. The one on the top actually has a black hole right in the middle. And how do we know there's a black hole? We see an extremely point-like object with very bright, and we say, how can anything that small be so bright? So then we calculate the motions of things around it, and we say, how we know the mass as well. So there's a black hole in there, and we see it because things are falling into it. Here's another beautiful picture showing what we call the cartwheel galaxy. This is now interpreted as a collision. The small galaxy in the upper left. See if I can use this. The small galaxy in the upper left. It went right straight through the middle of this big galaxy down here. And what we're seeing is the result of the collision. Material was splashed out, and the new stars were born in the ring around it. So right now it's a laboratory for us. We're able to calculate and simulate the formation of the new stars and the motions of the gas from this collision. Here is another galaxy that we point out seems to have holes in it. This is an ordinary galaxy. We just thought it was an ordinary spiral galaxy before. Now when we take an infrared picture, we see that there are holes, and there it looks like a slice through a sponge. So what would make holes in a galaxy? We think that it's because there are stars that are formed in these middles of these holes. And when they are formed, they produce so much energy that they push the remaining material away from them. So galaxy with holes. We never would have known this without the Webb telescope. We are looking at something people call the pillars of creation. This is a place where stars are being born as we speak. What we see appears to have a wind flowing from the upper right corner down towards the lower left. And the wind is coming because of new stars that have been born. It's like that little hole in the galaxy that I just showed you, but it is close up, so we can see individual stars inside this cloud being born today. One of my favorite pictures is this one. This is a star in the process of being formed. What we're seeing right here in the middle, it looks like a hamburger bun. The dark area across the center is where the new stars are being born. Excuse me, where the new star is being born with dust grains orbiting around it, like a new solar system, with the ecliptic plane filled with dust and planets growing in it. Light is shining up and down, illuminating the remainder of the cloud, and there's a jet of material coming out the north and south poles of the new star. So we see that, and now we'd like to know exactly what's going on inside. Astronomers now have something to work on to calculate all of this. So we are also looking at planets around other stars. Planets sometimes go in front of their host stars, as the little movie in the upper right corner shows you. When a planet goes in front of the star, you can say, I know it's there. If it comes back every 7 days or so, you know it takes a week to go around, and you can calculate its orbit. You can calculate its temperature because of the properties of the star and the geometry. So now we have calculations of the size and temperature of an object, and now we want to know, does it have an atmosphere? So if it does, some of the starlight goes through the atmosphere of the planet on its way to our telescope. And that makes it seem like it's a different size at each different wavelength. For instance, clouds in the upper atmosphere would make the planet look bigger, or molecules at certain wavelengths would make the planet look bigger at those wavelengths than at others. So we've been looking, we have at least 6 planets we've already looked at. And so far, all of the small ones, the size of Earth or a little bigger, seem to have no atmosphere. Larger planets usually do have atmosphere, and in fact, most of them, like Neptune or Jupiter, are so large that they have all atmosphere and maybe have no solid core. It's hard to tell. So at any rate, we are now using a technique that we can find out what is the chemistry of the atmosphere of a planet around another star. So far, we have many molecules. We have carbon dioxide, we have methane, we have ammonia, and we have water in some planets, just not in the atmospheres of any small Earth-like planets. Here's an example of one that shows not only the molecules I mentioned, but even sodium and potassium can be seen in absorption using using 3 of the 4 Webb telescope instruments to get spectra. And so we're very proud of ourselves that we're getting about the same answer with each different kind of equipment. We have been, of course, looking in our own solar system. Here is good old Jupiter, and we're showing you that it has several satellites of its own, that it has a ring, which you can sort of see here. It has an aurora at the north and south poles. It even has the effect of the satellite Io or Io, because Io is very close to Jupiter and is very hot and is sending out sulfur vapor that interacts with the ionosphere of Jupiter. We, as you know, attacked an asteroid. We dropped a large piece of metal onto this one. We watched it with the Hubble telescope and with the Webb telescope, and we learned that some debris would come out, and we also learned that we were able to move the asteroid about 5 times as much as we would have moved it if it were only a billiard ball collision. So this is helpful in our plans to protect the Earth from asteroids. We've been looking at Titan. Titan is a satellite of Saturn. And satellite of Saturn, that's very interesting because it has weather. It has a very low temperature. It's about 60 or so degrees Kelvin. So the weather there is made of hydrocarbons, ethane and methane. We have lakes, rivers, clouds, rain, all made of ethane and methane. And so we are sending a small helicopter called the Dragonfly to land on Titan in another decade or so. So right now we're just trying to learn about as much as we can about Titan and its chemistry and surface before we go. Just a couple more beautiful pictures. Here is Neptune, seen with its very bright satellite in the upper edge of the picture, and many others with ancient mythological names attached. And here is Uranus, a similar picture. Uranus is special for us because it's the only planet in the solar system where the spin axis is in approximately the orbit plane. So that means that sometimes we can see the north or south pole of Uranus directly. In this case, the satellites are labeled with names of Shakespearean characters. So there's a lot more to say. You can follow along with the Webb telescope data on our own websites, but because we are so popular, there's a news event every day from all of our media. And so I hope that you're finding excitement these days in the news media, as well as looking at our direct websites. And if you want to propose to observe with the Webb telescope, you have to send us a proposal. But everyone is eligible to propose. So maybe I'll stop here. There are many more questions we could address, but it's a good time for questions. So let me ask 4 questions. And Anis, would you like to run that process?
Yes, sure. Well, first of all, thank you so much. We can never learn enough. So at least we have, as a layman, we have the background. So let us open the floor for questions. And please ask one at a time. And I think for the process, let me ask one by one if you have a question. So maybe we should start with Dr. Khalid from Toronto. He's a medical doctor, but he's very curious about all of these things. Dr. Khalid, do you have any question or comment? Please be brief. Unmute yourself.
Yes. Can you hear me now?
Yes.
Yes, I do, Khalid.
Sorry, Dr. Mehta. No, my question is basically the JSWT can block out most of the infrared rays. Why can't the Hubble do the same? Why did you have to make the Webb when we could have put that little extra app in Hubble? Why do we not have it in the Hubble?
Okay, the most important thing the Hubble doesn't have is cold. So the Hubble is warm enough that it emits a vast amount of infrared light itself, just as you and I do. So you can't build a telescope that works well when it's emitting its own signal. So the Webb telescope is cold. It operates about 40 or 50 Kelvin in different places, except for one of the detectors, which runs at about 7 Kelvin. So that's why the Hubble could not possibly do this work. And similarly, why you cannot do it from Earth. Because, of course, here on Earth, everything is warm and is glowing with infrared light.
I have one more question, please.
Okay.
Where you showed the L1, 2, 3, 4, 5, the different positions of Laureate, you said something very significant, that at certain positions, the Webb telescope cannot visualize because of the shadow of the Earth falling on it. Now, if that is so, that means the telescope is not working 24/7 for us, is it?
Well, actually, no, we have chosen an orbit where it orbits around the shadow spot. So it's never in the shade. So it always is working.
Okay.
Wonderful. We have Dr. Shafiqul Islam Bhuiya joining from Dhaka. He just retired as the chairman of the Atomic Energy Commission of Bangladesh. So,
oh my goodness, yes. So
yeah,
please
Dr.
go ahead. Yeah.
Yeah, Shafiq, if you have any question or comment, please go ahead. Unmute yourself.
You hear me? Mm-hmm. Well, thank you very much for the fascinating pictures that we have seen. Actually, well, we don't understand much of it. It's just like what we say in Bengali, Rupkatha. What is the English word of this? So, well, and that's, it fascinates me this when I read all these stories that going back towards the, what we say that we are going back to time. It's like a time machine. And I just wonder, someday, do you think it may be a stupid question? Do you think that someday it might be possible to see the great explosion? That is what happened in 10 to the power minus 43 seconds after the Big Bang.
Oh my goodness. Yeah. So the closest we can get is the image that I showed you with the pink and blue spots. That is the image of the universe when it was 400,000 years old. The early universe is opaque. So light does not travel in a straight line. So it cannot travel at all until the universe becomes transparent at the age of 400,000 years. So that's the best we can do. The rest we have to calculate and imagine.
I just wonder if the technology will evolve someday that we'll see.
We can hope, but there is actually nothing we have in mind that we could possibly do.
Is this the redshift or other physics in it?
Yeah. So the picture I showed you with the pink and blue blobs is from a redshift of about 1,000. But that's not nearly far enough to go all the way back to the very first moments.
Wonderful. Yeah, any more questions, Shafiq?
No, it is okay. It is just like a
wonderful.
But anyway, it's the reality. We can imagine the vastness of the universe, and we understand that still we know very little of it, very little. And about this, if you would just say something about this black energy and the expanding universe. So the black energy, is this the fourth or fifth energy that that is expanding the universe? What is the energy behind this expanding universe?
Yes, so actually no one really knows. What we have is observations that we say, yes, the universe is expanding. We have observations that say it has dark matter in it, transparent matter, which has gravity but does not do anything else. It has the dark energy, which causes the acceleration in recent times. And these are all done by calculation. We cannot actually see them because they're not luminous. All we can do is report that we have deduced that they must be there.
So we can never reach the expansion because it's accelerating more than light. So the speed of light. So we will never get this. But
yeah.
I was, well, you told me just right now, you were telling me that the dark energy may be responsible for the expansion. Is there any scientific proof that the dark energy is responsible for the expansion?
Yeah, we have quite a lot of proof, and there was enough that a Nobel Prize was given for discovering and measuring the dark energy. and it's been confirmed in about 5 different ways. So we're pretty sure it's there, but we don't know what it is. All we have observed really is the acceleration. So Einstein had a place for it in his calculations. And so as far as we know, what we see fits perfectly with his calculations. But nobody knows why it's there.
Okay, so let's move on. I think Kazi Bhai has a question. Please unmute yourself. Yeah, go ahead and unmute yourself and ask a question.
Thank you. This is a fascinating talk. I didn't understand, I think 50% of it, but I have got one question about the existence of life elsewhere in the universe. I know that we have discovered a lot of planets this way, but based upon the findings that how many you have, how much space you have observed, and how many planets you have found, what is the prediction that there is, what fraction of the planets actually might have some of these things in the universe, so the life would actually exist like us?
Yes, we have found that most stars have planets. Most stars have several planets. And about 20% of all stars have a planet about the right size and temperature to be like Earth. We have no information yet about whether any of them have the right chemistry. So, but we have, of course, the one observation that Earth is alive. So, and we also have one observation that says it did not require very long for Earth to become alive after there were oceans. So we had no oceans that we know of from geology for about 500 million or 1 billion years in the Earth's history. And then within a few 100 million years of the first oceans, we have fossil evidence of life. So that says that perhaps life is common because it happens quickly. In that case, then it just is a question of what places are compatible with life, what places could have life. So my guess is purely a guess, because we have no measurements, is that there will be life in every planetary system, because there will be somewhere wet in every planetary system. Maybe it will be under an ocean, maybe it will be in the rocks underneath the surface, and maybe the life would be impossible to find from here, but I think there will be life in every planetary system. That's my guess.
And another related question, that our life is carbon-based, but is it necessary condition to have life?
We do not know what is necessary. So it's purely a guess. My guess is that if there's an ocean, there is life. If there's water, there is life. And liquid water. And how would you know? Well, we have the possibility of discovering oxygen in the atmosphere of another planet in another solar system. We would say, possibly photosynthesis. We have the possibility of visiting other places in our own solar system, Mars and Europa and Titan and Enceladus. There are possibilities of liquid water there. And if we could find some samples and get some information about those, then maybe we will know that there's life elsewhere here in the solar system. So those are the two big possibilities for us.
Thank you.
Wonderful. Let's move on to Dr. Sufyan Khandekar. Sufyan Bhai, if you have any question and comments.
Thank you, Anis. It's a very fascinating presentation by Dr. Mathur is beyond me. I'm a simple engineer, deal with water resources, floods and things like that. For me to go to the sky is kind of very fascinating. But the picture and the story, the way you have told it, very simple way, it really created lots of interest in the presentation. The few of the questions, of course, the outstanding question everybody asks is the existence of life in another planet. Again, the answer is, as you gave, is probably the correct answer. I'm going to switch a little bit that there are lots of talk in these days regarding the UFO or EFE, whatever it is. And particularly recently, Mexico was showing some pictures and claiming that these are from the outer space. Can you make some observation to those?
Okay, well, good question. I have no specific information about those reports, but Enrico Fermi, famous physicist, asked if long-distance space travel is possible, where is everyone? So where are those visitors? So there are two possible answers. Well, one is long-distance space travel is not possible. One is that those kinds of civilizations that could do it are too far away. So I think on my guess is that long-distance space travel is impossible for biological beings like ourselves. At the speed that we could go, it would take 100,000 years to get to Alpha Centauri, where there probably are planets. So in 100,000 years, we would be dead. We cannot survive that trip. So even robots that we could build would be tired after 100,000 years of travel. So I don't know what we've seen locally. I don't know about the reports from Mexico, but I do think it's unlikely that they're coming from space aliens.
Okay, let's go to Dr. Shabir Parvez. He is familiar with satellites. He has a company who does with satellite and probably a little bit of imagery. Shabir bhai, you have any question or comment? He's probably muted. I don't know if he's listening. So
okay.
He's probably not listening. Anyway, so then we also have Mr. Muntazir Rahman. He works for Riva. Riva is a well-known company, makes the imaging and spectrometer. And if you have any question, Muntazir bhai, please unmute yourself and ask.
Thank you. Thank you for giving me the opportunity to ask a question to Dr. Mathur. Well, my world is completely different from what I heard from today's presentation. I am involved in chemical sensing of especially the gases, compounds. So it's a light absorption spectroscopy. Most of the time, I use some different wavelength of lights and a detector, normally the MCD detector. Sometimes it's remote sensing. So I was wondering, how can I actually correlate my work with Dr. Mathur's work to find out compounds in the space?
Well, good question. Number one, I would confirm that we use the same kind of detectors, more or less. Mercury cadmium telluride detectors are excellent detectors for astronomy. And so we have spectroscopy on board the telescope with a spectral resolution of about 3,000. which is enough to distinguish one molecule from another if the spectrum information is there. So we've detected quite a large number of different molecules in space, either because they appear to emit extra light or because they absorb light at particular wavelengths. So we use the same or similar technique to what you do to see molecules in a gas. So it's pretty similar, I think.
So thank you. So
Yeah,
in my case,
so just a curiosity that is it only the gas that you are interested in, or studying these space rocks and meteors and stuff like that? Could that give any similar information by any chance?
Yes, we do study the solid phase also. Dust particles can be seen, and we already know that some of them have spectral features from ice of various kinds. Water ice, ammonia ice, carbon dioxide ice, all have different spectra, and we can recognize those in some objects, particularly in places where stars are being born, in the outflows from new or old stars, and in comets, where those molecules will be coming out along with dust grains as the comets are disintegrating in the solar system. So we indeed do look for solid phase as well as gas phase features in the spectra.
All right. Now we also have Professor Afzal from Truman University. Professor Afzal, if you have any question or comment.
Well, I used to actually teach a course called The Origins of Life as an interdisciplinary course where we used to look into all sorts of possibilities. But again, the whole thing comes from the fact is if the chemical conditions are ideal, life would happen. But we haven't come across any real examples yet. So that's always an interesting case. What would we find? Yeah.
Okay, I don't know if there was a question or just a comment.
The question is, what might be? I mean, is the oxygen or the carbon would be the signature for life?
Nothing as simple as a signature. Okay. Oxygen is a clue.
Yes.
Because here on Earth it's very reactive.
Yes.
And it would only exist for a short time unless it was continually being produced by plants and algae. So, but if you see a lot of oxygen in another planet, it's still not quite enough. You have to consider the possibilities of other sources of oxygen. So we shall see.
And the liquid is also a requirement because the chemical reactions that are required for life cannot happen in solid phase, probably.
I think that's true, but I'm not a chemist. I'm not a biologist, so I'm just sure. Guessing about that.
Wonderful. I have one quick question, and that's about the imaging. The IR, the infrared, made the magic compared to the Hubble's visible spectrum detectors. That's because IR detectors are slightly different. They work in bigger wavelength. And of course, we know the diffraction limit is still applies to any wavelength. Now, so if for the moment, if we think that diffraction limit somehow magically or whatever could be overcome, then opening up even bigger wavelength, would that have any benefit for space imaging?
Well, my goodness, there certainly are ideas for improving angular resolution. The traditional one is to build an interferometer, which is an optical instrument that's like a telescope, but without the whole mirror. So just pieces of the mirror collect some of the information, and then we can use some of the information to get the image that we want. So it's not quite as good, but it's very powerful, and we do use them. When, for instance, you saw the images of the black hole, that were made a couple of years ago that was done with interferometer techniques, where we have a few antennas, about 10 of them, in different places on Earth, and they recorded the waveforms on hard drives, and they brought them together to a computer, and they correlated them to make an image. So it's a huge accomplishment, and yes, it's possible to do it that way. There are some very imaginative proposals regarding quantum storage of light, and I think that's too difficult for me to anticipate what will happen. It's not logically impossible, but I don't see how it could happen.
Well, is anyone else have any other question or comments?
Yeah, I had a quick question.
Yeah, please.
Again, through this discussion and some others also, we understand that the extended universe, the universe is extending. Now the question is that relatively, suppose our solar system, we have a distance from the sun to the earth as of today. Is that distance is being expanded also? If that is true, what are the consequences? Because at this distance, we get certain amount of energy, heat, all those kinds of things. If that varies, then what are the consequences of that variation? Or what is the end result of this expansion, continuous expansion to universe or the planet system?
Excellent question. In fact, we have been working on that for a long time. So we have a measurement, of course, of the distance to the moon. We do that with laser pulses that we send out from observatory on the surface of the Earth, and we can measure the position of the moon within a precision of a millimeter by the laser pulses. Apollo astronauts left some reflectors on the surface of the moon just for this purpose. And the answer seems to be no, there is no effect of the cosmic expansion on the orbit of the moon. So big question has been answered by measurement.
Okay, any other? Yeah, go ahead.
So I said the relative distance between the planet or the sun and the earth is not varying much. Is that the reason?
Yes,
that
that's correct.
We don't expect much changes because of that?
That's correct. They're all very tightly bound together by gravity. Ordinary gravity, according to Isaac Newton's form, is sufficient to describe what we see in the solar system with very small corrections for relativity. So as far as we are aware, the cosmic expansion does not affect the orbits of planets in the solar system that in a way that we could measure.
Thank you.
All right, so we are coming close to our allocated time until 3 p.m., but we still have a few more minutes. If anyone else has any more questions or comments, please feel free to ask. Otherwise, we may come to close.
If I may, please.
Yeah, please, go ahead.
My name is Mohammed Abdul Rakib from Essex in England, and I'm very happy that I'm participating with you guys. I'm not a physicist now, rather I'm a chartered accountant retired. But I have a question for Dr. Mather, the Nobel laureate. It's the light and the wave particle duality. I still cannot understand it. How light, which is a wave, and which is a corpuscle or particle, when you are looking at it, it behaves one way. When you are not looking at it, it behaves another way. I know it's a very basic question, but it puzzles me, like this fine structure constant that used to wake people up. People like Dirac, people like Feynman. I was very fortunate to be at Cambridge, Cavendish Laboratory, where probably the last Nobel laureate was Professor Mott. And And then recently, probably Roger Penrose has some connection with Cambridge and he's Oxford-based. So really, with that in mind, is there a good reason why quantum mechanics and relativity and this wave particle duality, so basic, should behave like this? In my youth, probably I should say in my while I was a child, in a village, remote village in Bangladesh, I used to walk and I used to see some sort of leaves. I don't know what you call them, but as soon as you touch them, they would close. So that means when you are seeing at them, they behave one way. When you are away from them, they're completely free. Is there a correlation of some sort between the wave and particle aspect of light? Thank you very much.
Oh, my goodness, you're asking one of the hardest questions of physics. We have observed that light can behave as a wave, and we've observed that it can behave as a particle. And we have all the equations necessary to calculate everything about it. Yeah. But it's still very puzzling to all of us because we are so used to thinking of particles as the explanation for everything. A particle occupying a place in space and having a particular velocity. And nevertheless, we know that's not good enough. So people are making some progress on trying to see why a wave description of things still acts like it has particles in it.
Right.
Always. So I think ask again to people in the future, they will have a better explanation for it. Right now, we are just, I think almost everyone is puzzled about how is it possible that we have both wave and particle behavior of the same thing. And the wave nature tells you that something is not localized.
Yes.
You cannot say it's a wave is here. A wave only exists in space. So here's a related question. If you're a mathematician, you probably studied analytic functions and complex variables.
Yes, I did.
Yeah.
Once upon a time.
There's a puzzle in that one too. An analytic function is entirely determined by its behavior on a short finite interval of its input value. So the analytic nature of the complex variable is quite surprising to all of us. So even ordinary mathematics has big surprises in it before we even get to physics.
I see.
Yeah.
Oh, we got Sarah Tasnim Bhavi come back. She's the chairman of the Department of Computer Science in Connecticut.
Ah.
So I don't know if Leo Bhavi has any question or comment. Please.
I don't have any question. I am not up to that level of asking any question to Dr. Mathur. I just wanted to express my gratitude to deliver such a wonderful talk to Bangladeshi American community.
Well, thank you, Dr.
Thank you so much.
Yeah,
thank you.
Yeah, I'm happy to be able to do it with you.
Yeah, it's a great, what do I say? I'm humbled to speak to you. Yeah, and I teach at a university in Connecticut, Eastern Connecticut State University.
Okay.
It's a teaching university, and I teach computer science, originally from Bangladesh. And just wanted to mention, very recently, me and my colleague received a NASA Connecticut Space Grant.
Oh, that's excellent news. Congratulations.
Students, yeah.
Congratulations.
Yeah, thank you so much. We have involved 2 students, and we are doing artificial intelligence, like convolutional neural network image classification.
Oh, wow.
Yeah, right. We are all working on that. I'm sure you know about AlexNet and ResNet. Those classification networks are classifying images Earth images, Mars images. So we are trying with our undergrad students.
Yes. So, by the way, there's an astronomer I know from Bangladesh. Do you know Sakhu Vertalek? She's at the Center for Astrophysics in Harvard.
Oh, yeah. What's the name once again, please?
Sakhu, S-A-K-U, Vertalek. She's married to a guy named Vertalek, V-R-T-I-L-E-K.
Okay.
Yeah, I think we heard the name. I haven't met him yet, but we'll find out more about it. And echoing Professor Tasneem, we really would like to express our gratitude to Dr. Mathur for his kind appearance here, the time he took, and all the things that we are learning from him. He took the time to educate us. It's really an honor and fortune for all of us. I hope Dr. Mathur will come back to us again and educate us some more on his never-ending journey of space exploration. And this is so fascinating and so exhilarating for our community that people who came from Bangladesh. I came some 40-some years ago, and ever since started learning whatever little I can, but yet we have not been able to make any significant contribution. So this kind of inspiration for our community is very important, that someday maybe some Bangladeshi American will make some contribution in science and technology.
Well, probably many of them have. You just don't know who they are yet. So I put a website for Sakhu Vertalek in the chat.
Oh, thank you very much.
You can read about her.
Sure, that would be wonderful.
She's my friend also.
Yeah. Okay, so any last comment from anyone else? We came to the end of our allocated time.
I have a quick question.
Yeah, please.
The number of Goldilocks planets, or the habitable zone planets, that our knowledge today is much more than only a few years ago. And more planets are getting into that list. So what's our resolution? How far can we look into the stars to look at for these kind of a habitable planet zone?
Well, right now we're seeing them orbiting around M stars. Are small stars about the size of planet Jupiter. And most of those are not likely to be friendly for life, because the stars are very active and send out blasts of material into space. We need a new telescope, much more powerful than what we have, to be able to see an Earth-like planet orbiting around a star like the sun. So ask it again in about 20 or 30 years, we may have an answer for you.
Thank you. I always had that question, because when I started teaching the course, we didn't have much, but within the time frame of 10 years or so, many showed up, like the Goldilocks planets, and you have to have the right kind of temperature range and gravitational power and atmosphere and all these things to make it a Goldilocks planet.
Yes. So right now we think about 20% of stars have a Goldilocks zone, where the planet's the right size and temperature. But we don't know anything yet about atmosphere. Okay. Well, thank you all for your thinking with me, and best of luck in your explorations. And Anis, thanks for inviting me. It was fun.
I'm so fortunate that you were so kind to accept the invitation and spend the time with us. We are lucky and honored, and we hope that this tradition continues. I met Lee Feinberg as well, so maybe he might be our next guest, but we're trying. We're pursuing him.
Okay, excellent. He's wonderful. So anyway, thanks again for inviting me. It was a pleasure to talk with you.
Thank you.
Thank you from Bangladesh.
Yeah.
Dr. Mathur.
Thank you. And here is a British Bangladeshi. British Bangladeshi physicist turned accountant, and now I'm coming back to physics, hopefully.
Okay.
Thank you.
Many successful adventures. Bye-bye.
Thank you all.
Bye-bye.
We'll see you soon again.
Bye-bye.
Bye.